My name is Gabriel Mazetto. I'm a Brazilian, but I'm living on the beautiful city of Amsterdam, where the weather is always good and there is always sunlight. There's never rains. It's actually quite the opposite of that. I work for GitLab. I work for GitLab as a software developer, as a backend developer. Um, I'm part of the GitLab Geo team. At the GitLab Geo team, we create a geographical replication solution that is able to replicate your GitLab instance from one location to the other location. We also have a disaster recovery solution that is part of this team, but that's not what I'm going to talk about today. As you may have figured out, in GitLab, when you are creating an issue, when you are commenting, when you're doing contributions to a major request or an issue or somewhere else, you're probably writing your text as a plain text or as a Markdown file, or a Markdown syntax. And as a Markdown, that's actually what we're going to talk about today. So to actually be able to render that Markdown file, we have to have a Markdown implementation from our software. And we actually don't use the generic Markdown or common Markdown or anything like that. We have our own flavored Markdown with specific syntax, extensions, and improvements. So the talk today is about building your own flavored Markdown with Ruby. Let's start by talking about what is actually Markdown. So Markdown is intended to be an easy to read and easy to write text to HTML markup language. And by actually looking at this formal definition, we kind of have some questions. What is actually a markup language? So a markup language is a system for annotating a document in a way that is syntactically distinguishable from the text itself. So this is again a formal definition. What it's actually trying to tell you here is that you should be able to annotate your text content with something that you can distinguish from the actual text, and you can get you can add meaning to that thing. For example, if you have a regular markup that everybody knows and understands, HTML, when you add a specific annotation there with URL to an image, that annotation tells to the program that is reading that document, that it should, instead of just displaying the URL itself, you should display the image, should render an image. So a markup language is usually targeted to an application and to be processed by an application. So this is how a regular Markdown looks like. So we have, for example, on the top of it, we have the simple definition of a title, and it's followed by just regular plain text that may look like normal for you right now, but if we just add some syntax highlighting to it, we can actually discover what it's all about. So for example, again, we have here the definition of a title. We have a strong annotation here. So this is should be rendered as something, for example, as a bold text. We have some other formatting here, adding emphasis to part of the text. We have a hyperlink pointing to this specific URL here, and we have at the very bottom of the example a Ruby snippet. So we are annotating the whole file, adding meaning to it, that we can still read it as a plain text, but if this is processed, we can give a very, very improved output to it. The next thing that usually goes together with Markdown is the text to HTML conversion. So Markdown was not supposed to be read in its final form as a plain text. So usually you want to convert it to HTML so you can actually render and visualize it in a browser. So let's try to convert a very simple Markdown document. We have the simple input here again. So it again has some specific annotations. So for example, this is an emphasis. You add emphasis to your text by adding a underline annotation on the beginning and on the end of either the word or the phrase that you want to emphasize. The same can be done with the star symbol, the single star symbol, and if you want to have like the very big strong impact, then you add 2 asterisks, and it will be usually rendered as a bold term. So the expected output goes in HTML, so emphasis tags, opening and closing, and strong tag, opening and closing. If we move forward to that example, we can extract some rules from this experiment. For example, as we talked about earlier, the first rule that we can figure out is that anything that is surrounded by either underline or a single asterisk should be modified to emphasis tag. The same goes for the second implicit rule. Anything surrounded by 2 asterisks should be modified to be surrounded by strong tags. So let's see the place where we should modify the text again. So if we start to parsing the text, we see that the squared annotated parts as the place that we want to modify. As a tentative solution, let's try to do the simplest way that we can achieve the result, which is by using find and replace. So there's a little bit of Ruby code, but it's not essential for the presentation. But let's take a look at it. So this is where I define the content. It's the same thing that we saw before. We continued by using the gsub command, which is a command to overwrite anything that starts with underscore with em tag, and it goes globally, so it overwrites the whole text. We're doing the same for single asterisks and the same for double asterisks. And if you take a look at the final output of this implementation, we were able to add the emphasis tag, and we are not able to add the strong tag, and we are also not closing it. So this is not the perfect solution. So let's take a look at another tentative. As we saw in the previous example, replacing it was kind of easy, but we're missing still the closing tags, and the strong tag was not able to render because the order is actually important. So let's try to invert the order. And we saw that the order that we process the rules does matter. This is really important. So the second tentative, we modified the substitution instruction to be the first one. So we got the correct output here. We're still not closing the tags, but we managed to get the strong annotation, and the emphasized one are still correct. So how can we keep improving this code? So this is the third tentative. It's the same content, and now we try to do something a little bit different. Instead of doing 3 different calls to the substitution command, we are using a very simple regular expression here. So we're still looking for the same double asterisk or underline or single asterisk, and using some powerful APIs from Ruby, we are able to say, okay, if you find 2 asterisks, change it to strong. If you find 1 underline, change to emphasis. If you find 1 asterisk, change to emphasis. This is again a visualization of what that command did before. So it found these small tokens that we said that to Ruby that it should find, and it changed it then to the terms that we said that we wanted then to change. So we still need to improve this. We discovered that in our first tentatives, we can simply use find and replace, as the symbols are actually ambiguous. When you see the first underline or when you see the first star symbol, we're changing it to emphasis tag, but we can actually program the replace. Okay, when you find the second one, then do that. So we need a different approach. What we would actually want to have is some kind of either a memory or some kind of state or variable that we can say, okay, if we are just parsing that text like a small cursor, when you find the first symbol, we save that state in memory. Then when we find the second symbol, we read from memory, and then we know that we have to change it in a different way. But instead of doing this manually, let's try to actually use regular expressions with patterns. So this was our first regular expression. Again, it will match all these single characters without holding any type of state. So we actually need something a little bit different. We need to actually create the pattern that we want to find. So for example, in the first case, we want double asterisks surrounding some kind of content in the middle. And the same thing for the single underline and single asterisk. They should be surrounding the internal content. When taking a look at the regular expression, I want to try to explain to you a little bit of each part of it. So we start with this pattern here, and it is surrounded by parentheses, which means it's a capture group. A capture group is something that after the regular expression is processed, it will return to the Ruby script as something that you can actually change or do operations to it. So this is something that the regular expression will return. We have in the middle two special matchers. The first one is the dot matcher that matches any type of character. And it's the asterisk following it means that you should repeat that matcher 0 or more times. So what it's doing here is that after it finds the first pattern, it accepts any kind of character until the end. We also have the logical OR, where in the other example, so we are matching each the underline or the asterisk. And in our fourth tentative, we are using these previous regular expressions. We are using a special regular expression feature, which is we are reusing the second match group here. So that is the /2. So whatever it finds here, it will be replaced here. So for example, this piece of code will find the double asterisks, anything in the middle, another 2 asterisks, and it will replace by strong opening the content in the middle and strong closing. So this is the result that we got. It works really, really well. So we had the strong opening, the important part, and the strong closing. But if we look at the second example, there's something that doesn't look quite ready here. So we have the emphasis opening here. We don't have it here, but then we have it closing at the end. So you may start to think, okay, what is wrong here? This is the same output, so we can visualize it a little bit better. And what's going on here? So again, let's take a look at this regular expression. So this part in the middle is actually the problem. The asterisk is considered a grid operator. So what means by a grid operator? When the regular expression is being parsed, it goes from the beginning of the first match until the end of the text. So that's what the grid operator does. And because it's not finding the other part of the regular expression, it fails and then it backtracks. So it tries to remove the last character and then evaluates again. And it fails again, and then it removes the last character and evaluates again. So this is expensive, and this actually doesn't work really well. But it explains what we saw here. So when it found the first capture group here, it went to the end of the text. It didn't find the last one, and then it starts removing every token that it finds after. And when it actually found the match group that matched the pattern, then it ended here. So that's why we missed this. So this is the improved version of that regular expression. So we need to add this question mark here. And what the question mark does, it changes the grid operator into a lazy operator, or what people usually call ungrid operator. And what it does is, when it starts to evaluating the dot, it goes the first character, and then it tries to evaluate the rest of the regular expression. When it fails, it backtracks, but it backtracks forward. This is the correct term. It's misleading, but that's the correct term. So then it goes forward and tries to evaluate the whole regular expression until it finds the first closing token. That's what we are looking for. And by changing our initial 50 tentative into this new regular expression, we actually get what we are looking for. So the emphasis is opening and closing correctly here, and also here. So yeah, success. But we can still improve it. As you can see here, there is still a problem. With this regular expression, I can start it with underscore and end it with asterisk. So this is not ideal. There are a few ways to fix this. You could make one regular expression with just the asterisk, this capture group, and then the asterisk again, and pipe it to OR and do the same thing with underscore. Or you can just do this. We are still reusing that capture group here, and we are using it inside the regular expression. So if we find underscore, it will be underscore here. If we find asterisk here, it will be asterisk here. But as you can imagine, things can get a little bit complicated if we consider block level markups. So we're just formatting a few words in the text. But if you take, for example, this Markdown, what should we do here? So if we just reuse that previous replace rule, the output will be incorrect. It will be a bold or a strong HTML here, which is not ideal. And also, how the hell are you going to parse this table? And it also have this conflicting syntax here. There's formatting as well, so it gets messy. And the way to fix this, it's not actually to keep the simple finding replace. So let's take a look about how can we use compilers to help us here. Compiler is a program that can read another program in one language, the source code, and can translate it into an equivalent program in another language. So this is the formal definition, and usually use a compiler to get a source code into machine code. A compiler has some fundamental parts. We can start it by looking at the lexical analyzer, which is usually the scanner. This is the part of the compiler that actually reads the source code and do the initial transformation. We can have, after that, the syntax analyzer, which is usually implemented in the same part of the code. You usually have scanner and parser doing the same thing, but the syntax is more, it cares more about the relations of the pieces in the source code. So it's not just trying to do the pattern matching here, but it's trying to actually interpret it, what it's reading from the source file. And then you have semantic analyzers, intermediate code generation, code optimizer, and etc., etc., etc. So this is actually the diagram that describes a traditional compiler. So you usually start with the source file here, that it's fed into the program input. This is your file reader component. The file reader component will feed characters to the lexical analyzer. The lexical analyzer will get these characters, do pattern matching there, and provide tokens for the syntax analyzer that will transform these tokens into a abstracted syntax tree. The abstracted syntax tree is used to do context handling, add annotations to it, and then it moves forward the pipeline. So you have intermediate code generation, you have all steps of optimizations, you have the first code generation part, and then you have target code optimizations until you get to your final binary code here on the other end. But we don't need all of that. We just need a slice of it. So let's take a look again how a generic Markdown to HTML transpiler looks like. And now I'm using the term transpiler because this is the correct term. When you have, it's not just simple converser. So we start again with a file that is fed into your file reader. It provides characters to a lexical analyzer. The lexical analyzer transforms those patterns into tokens that it's again go down to the pipeline until you have your HTML actually converser and your final HTML document. But the most important part here is actually the lexical analyzer. It's the most difficult one to implement. So to actually understand and see a real life example. The lexical analyzer is also known as the scanner, and a scanner needs to identify only a finite set of valid tokens or lexims that belongs to the language rules. So again, this is a formal definition. We're still talking about compilers, but we're trying to move this to the real world. So just so you can understand a few glossary terms, a token is actually a string annotated. So it's a tuple, and it has a type, and it can optionally have a value. And a lexeme is the actual word that you can do the pattern matching. So you usually have lexeme as part of the token. And let's take a look at the simple scanner example, target to Markdown. So here are our rules. This is the very, very simplest example of a scanner that provides words. So it will read a ASCII text, and it will provide only the words. So we know that it's separated by white space, but we are also adding the rule that if there is a special character, we are also considering it as a space. So for example, if there is a comma or a point, we don't care about it. We just care about the words. If we create the BNF grammar definition for our scanner, it will kind of look like this. So this is the starting point. So we start with the content that is formed by either a word or a separator, one or more words. A word is formed by one or more chars. A char is anything from A to Z in lowercase or capital case. And the separator is formed by all these symbols here and space. Again, we're still talking about the lexical analyze. This is actually how it looks like when a scanner runs. So it goes running this cursor around the text. It identifies the patterns that we saw before. So we wanted it to output all the words and all the tokens that it found. But we know, for example, that asterisk is not something that we want to return. So this is just a separator. We will ignore it. And we need to annotate it to form a token. So this is how it looks like. For example, here we are annotating it with the position we found it in the string. So the word this is found at this starting point 0. The word text is found at the start point 5, and etc., etc., etc. This process is called the tokenization. The final representation of these tokens can be seen and can be expressed in many different syntax. We can express it in XML syntax, but the most common one is the X expression. So it starts with the content. It has the word this, the word is, the word a, etc., 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 and it closes the content here. So this is our input, and are the tokens that this scanner can identify and can provide to the next step. The next step is the abstracted syntax tree. The next question is, okay, why compilers have an abstract syntax tree? So after the tokenization, tokens are converted to a tree structure, which is the AST, and they can be annotated with information required by later steps. A few use case examples are error handling. For example, if there is an issue with the syntax, you need to know the file and the line and probably the position in that line that the error is there. So you can provide the error output to the user. So you need to annotate that token. Another example is doing dynamic typing inference. So if you have a language like Ruby or Python that can have dynamic typing, usually you need to annotate that the types definitions that you read from the source code into the AST, so it can be used by later steps. It can also be used by to de-ambiguize ambiguous grammars. For example, when it's an opening or when it's a closing tag in the Markdown example before, and you can manipulate the ASC to do transformations not on the source code level, but as an object in the memory, and so on. Other examples here, more Markdown oriented, are, for example, if we find a header, we want to actually annotate if this is the header in the level 1, level 2, level 3, etc. And the same goes for images. We may have a pattern that finds the URL that it's marked as an image, and then it can be followed by some syntax definitions that define the alternate text. So we can probably combine those two in the same object into the AST, or we can do transformations. For example, instead of getting the full URL, just transform it into relative URL. And you don't want to do that on the source text, the source code. You want to do that with real objects or with hashes or arrays, etc. So that's what the AST is used for. How can we use that in real life? Again, going back to the Markdown example before, this is a screenshot of our documentation site. Our documentation site actually uses GitLab flavored Markdown. It's the same Markdown that we have implemented on the Rails code, but it's not the same code that is inside the Rails code. And we can talk about this. So our documentation site is also open source. It's running, I think, okay, the description here is wrong. It's not using nano-C anymore. It's using middleman. And we can share the same code that's running inside the Rails app, because we have we do other operations that we can do here. For example, we go to the database to see if you can actually have the visibility to see an issue, or if the handler that you market there actually exists on the database. So we do some smart things there that it's hard to port to another software. To actually fix this, we start with the idea of the GitLab Kramdown gem. So GitLab Kramdown is an extension over the Kramdown gem, which is again one of the many different Markdown implementations. So many things that we talked here before were instrumental to actually understand the Kramdown implementation. Again, the Kramdown can be mapped from this diagram to actually Ruby classes. So we have everything from reading the file, or actually you provide the content. It goes to a lexical analyzer, a syntax analyzer, then it's sent to an HTML converter, and we can have the HTML document at the end. The most important class is the Kramdown parser, and the Kramdown parser has a specific differentiation on how the tokens are parsed, or on how the source code is read. It have a specific span parser, which is what we used before to transform the asterisk into a strong annotation, but it also has a block parser, which is used to fix the issue with what we should do when it's a source code. So should we still keep applying the strong conversion pattern, or should we do something different? For example, doing syntax highlighting. The parser delegates this pattern matching to a Ruby class called the string scanner, and it also generates the AST in the form of the Kramdown document and the Kramdown element. So let's see some source code. This is Ruby code, but it's very simple. I actually want to show you just a few things. Let's see. Okay.
That means if a process dies, not share, it can be claimed.
Okay. So let's get this. Okay. Okay, much better. So the GitLab Kramdown parser, which is the most important part of the code, it overrides the Kramdown parser itself. We have a few extensions implemented here. For example, we have the autolink, we have reference, we have the custom way that we do the headers, etc. So we're starting by pre-painting the rules. So we have our rules running before the Kramdown rules. So for example, we have the commit diff syntax. Let's try to take a look at it. I think it is, or yeah, I think it is in here. Let's see again. So part of the code is actually implementing patterns using regular expression. So we need to define them. We need to define how to actually the parser will find in the source code, and we do the transformation. So for the commit pattern, here it uses the namespace definition, which is the always full namespace format regular expression, which is composed by other regular expressions. It has the commit matcher here, which is the important part, and it can be followed by 3 dots. So this is all the pattern definitions that we have here. We are assigning them to this specific symbol that the Kramdown use parser, commit, whatever, parser, parse user group mentions as part of the method name. So let's take a look at the parse commit. We are manipulating the scanner to do the transformation here. So the scanner runs in other part of the code. When it finds that specific pattern, it delegates to this method. We can get the position in the source code. We can have the line number in the source code. We use a special parameter that we have defined when we instantiated the Kramdown document. And we are reusing the namespace and the commit that we just found during the pattern matching before. So we form this reference here. We create a Kramdown element, and then we add this Kramdown element to the AST. So this is the most important and the most difficult part to do. So after you implemented the pattern matching, you have to do this transformation and create the AST. And the good thing here is because Kramdown already have the HTML converter, and we are creating the elements that this converter use. When we annotate this as a link, the converter will know how to handle it. So this is all you need to do to make the transformation from a commit annotation to a HTML link at the end. Let's take a look at some code snippets here. So on the terminal. Okay. So let's take a look how the Kramdown AST looks like.
So all of this is made possible because we got to abstract, got separation of and separation of things that can only be achieved by the line. So the greatest asset is access to correlate runtime. This is
Let's try another terminal here.
solve your problems. But it would be very powerful to set a vocabulary shared by the whole community of we have two different limitations. We just want that's the problem. That's the reason not to. No matter who you are, we're not with all the characters, not programs.
Okay.
All of those are cool, but you're not working. You can say that, well, it's just syntax, no programming, frameworks, and stuff.
Okay. So we're calling the Kramdown gem here. We are feeding it with a few Markdown examples. Let's try to create a Markdown document here. It's a lot of stuff, but let's try to dive into a specific one here. So let's get the documents. So the first one. This is how the AST looks like. So the important part here. The important part here is the root element. So the root element has some file information like the encoding, location. It points out to the AST. So if we go here and get the children, we start with the. This is a simple. This is a simple bold text. So these are all the tokens that we just talked about before. To actually see how this looks like by using the converter, it outputs the final HTML file. So let's go back to the presentation here. So this is an example of how the Kramdown gem works, and if you want to learn a little bit more, I suggest that you go to the project page and ping me there if you want to contribute, or if you have an issue or a merge request. I don't think we have time for questions, but you can find me outside. Thank you.